Okay, so this is lab 2, stacks and queues, and we're going to look at how do we actually use stacks and queues to solve real problems. All right, this is our first challenge that I'd like us to think about. And it's one that you've probably solved before if you've written C#. Parentheses and parenthesis-like operators have to be balanced. And I think you intuitively have a knowledge of what balanced means. But it might be a little bit hard to think about how would you would check that balance. So for example, we're looking at these operators, the angle bracket, the curly, the square, and the regular parentheses. Those are the 4 pairs of parenthetical operators, grouping operators that we're going to consider. So if I gave you a string that looked like that, would you consider that balanced? Yes. So this is what I mean by balance. If I gave you one of those, would you consider that balanced? No. Okay. What if I gave you that? Is this whole string balanced? Okay. What if I gave you that? No? Okay. What about that? Not balanced. So can you say in English some of the properties, some of the characteristics of a balanced set of parentheses? So the opening has to come before the closing. Okay? That's true. 100%. So you have to find the closing of one before any other closing. Is that what you're saying?
And then you have something like that or regular closing. And
Curly? This makes sense. So I have some examples here of is balanced. What we're going to do is our string can contain a lot more than just parentheses, but we're going to ignore all the other text. So even a string like this, where I've got int a equals new int array, and then parentheses, parentheses, right? Legal C# should be balanced if you just consider the parentheses. Yeah? Let's see. If you look at this guy, why is this not balanced? Yeah. All right, what about this guy? What's wrong with this one? The opening is here, and then this guy doesn't match. Yeah? What about this? None of them are closed. And what about this? Oops. There's no opening. Okay, so we understand. Yeah.
if there are no, does it get true or false? If you have a string that's would it return true or false? Technically it's balanced because there's nothing to unbalance it.
What do y'all think? I agree. Yeah, if there's nothing there, then that is balanced. We have to have some parentheses to make it imbalanced. All right, how do we do this? How do we code this up?
probably would want to be.
Given context clues, it would seem like one of these data structures might be relevant. But that's just context clues. Maybe I'm being tricky. It's possible. I'd love to be tricky. Can you think about how you're doing it in your brain? Let's look at this. Could you process each symbol one at a time and make a decision? Okay. I guess as we look at each one of these, tell me balanced, not balanced, or I don't know yet. All right. Looking at one, is it balanced, unbalanced, or I don't know? But there's more. So really, if there's more, then so that's an I don't know. Oops. What about as we look at the opening square bracket? I don't know. Closing square bracket. We don't know. Closing parenthesis.
It is not.
And how did you know? How did you determine at this point? You have an answer.
There was no open.
What data did you look at to determine that it was imbalanced? Did you look at this? So you had to look at all three of the previous characters to determine it? Ryan thinks he looked at the first one. I could see that. Like, the fact that we had an opening and a closing here, to me, it almost as if, like, this is equivalent to if those are just gone. Right? The decision is the same. Like, so imagine here, what if we had a really complex thing here with a bunch of other stuff? All right, missed that. Okay? You with me so far? Like, I wonder when we get to, let's see, it's this point, right? I mean, to me, it's a little hard to tell. Can we simplify this? I would say we can simplify this. If we have a closing and an opening, then I could almost just delete that. Opening, closing. I said it backwards, my bad. Opening, closing, that's solid. Let's just get rid of it. Opening, closing, okay. Opening, closing, yeah. Opening, closing, yeah. Opening, closing, yeah. I've got a closing. Is the previous thing an opening? Yeah, okay. I've got a closing. Is the previous thing an opening? I've got a closing. Is the previous thing an opening for this? No. So it's at this point I know that is not balanced. Does that look like anything to you? How so?
So when you get a closing parenthesis, you don't have to immediately put it in. You can peek at what it's stacked. If it is the closing, the opening for the one you're closing, then it's good, but if it's not.
That's a good question. And I would direct your attention to this. So for the purposes of this lab, I'm basically saying we get to build on top of linked lists and just deal with stacks and queues. Okay? But good call. Tristan, you got thoughts? I saw consternation or maybe just thought about this. Reflections on Ryan's hypothesis or idea? So you've got basically a list And what is your check? You're looking for a substring uh, of what? Of the so I'm imagining, okay, if you have this, yeah. Does your algorithm handle this? Wait, these are all brackets. Okay, yes. First step, remove everything but letters, but these characters and spaces. So we can separate these out. Yes. So now I've got this string of just brackety symbols. So, okay. So this has none that are right beside each other. So we would, you're saying that that would be false. Let's see. You're saying if we had you're saying we check this for the first open close pair. So we're going to search until we find this, and then we remove it, and then we start back at the beginning, and we search and find this one and remove it, and then we start back at the beginning, and we find this and remove it, and then we start back at the beginning, and we find this and remove it. We start back at the beginning, and find this and remove it. Okay. I can see how that could work. How many times do we have to scan the string? Yeah, 6 or 7 times. I guess it would be the number of pairs that we had. Ryan, you got a thought?
I was just thinking of this in terms of big O terminology, and it's like every time you go over the list of pairs, you're having to iterate over the list. You have to iterate over the list the amount of times has them. So kind of the big O notation would be O of it. Because you have to keep iterating over the list. No, that would be like.
I think that's it. I think that's n squared, actually. What do you think, Christian? About the time complexity of that? Does that, you think that's more, is that? Let's see, if you've got one of these, so you're scanning through half the string, and how many times are you going through half the string? It's half. So I think that's a n over 2 times n over 2, which you have that nice over 2, but you have an n times n. You feel me? I'm pretty sure that's going to be on the order of n squared, which we don't really like. is there a way where we could do it by just running through the list once? Because that would have to be linear in runtime. Does that make sense? To go through the list once? You think the method would be n squared? Or you think it would not be n squared? Okay, I think I agree with you. So I wonder if if a stack could help us out, like this algorithm that Ryan proposed, is what I had in mind. I think this is a classic stack kind of problem. So when we run into an open parenthesis symbol, what should we do? Like, basically, if we're ever in that I don't know state, then we should push it on to the stack, I think. So that's a curly. I want to push it onto the stack. I found another parenthesis, another opening parenthesis there. I found a closing parenthesis. So at this point, when I find a closing parenthesis, does this curly matter? This is your intuition as well. No, the only thing that matters when you find the closing is whatever's on the top of the stack. And one could imagine that you could push the closing parenthesis on top and then examine the top two items and see if they're matching. I don't know. There's a completeness feel to that, but I wouldn't code it this way. I think instead I would say when your current character, this is your current, when this is a closing of any type, I would like to say, does the current character, is it a closing parenthesis for whatever the top of the stack is? Which we could get by peeking. If it is, then we just found a closing pair. And in that case, we don't need this anymore. And we can get rid of the top of the stack and pop. Yeah? So now let's move to the next character, which is, in this case, this. So it's another one of those. Same algorithm here. If we peek the top, we've got a curly. Does a curly match a closing parenthesis? No, it does not. So at this point, we know it can't be balanced. It doesn't even matter what the rest of the thing is. Okay, let's try a different example. Let's try this one. What happens here? If we have open, open, open with regular parenthesis, square bracket, so we are going to push on, right? Whenever we find an open, we push it. Find another open, we push it. Find another open, we push it. At this point, we've processed our whole string. You can see this is not closed. What's kind of the algorithmic test here? What's our programming logic to say that because of the state of this stack, it is not balanced?
The length 0.
So think about how should the stack look at the end if it's balanced? It should have nothing on it. It should have a size of 0. So if you get to the end and there's something on it, if you get to the end of the string, it's not balanced. Apparently you had way more openings than closings. Okay. Is this algorithm making sense? It's like remarkably simple. Opening, you push. Closing, you check the top and see if it matches. If it does, then you pop. If it doesn't, it's not balanced. If you process the whole string, check the size of the stack and see if it's 0. There is, I guess, this one more scenario, which is, what if we have this stack and our current symbol is a closing? Our algorithm before was check the top of the stack and see if there's a matching opening. Do you see what's the top of the stack? like we don't have a top of the stack. So we need to check and make sure, because if you try to get the top of the stack when there's not one, you might just throw an exception. So we'd rather here say, hey, if you ever try to do a comparison and the top of the stack is empty or not non-existent, then that's a false. Does that make sense? So this is balanced parentheses. It's a fun starting exercise that I think I'd like to start in just a little bit. All right. I want to show you another thing that's a fun little mathematical oddity. It's called postfix notation, or we're going to make a little postfix calculator. We are used to writing math like this. And this is called infix notation, where the operator is in the expression. It's between the two numbers. So this is, you see, 2 plus 6 times 3. In postfix notation, we would denote this in this format, where we say number, these are called operators, and then operand, plus. And then we would take the result of the 2 plus 6, aka 8, and multiply it by 3. Mm-hmm. Mm-hmm. You feeling this? So anything you could write in infix, you could write in postfix. This is also called reverse Polish notation, because I think some Polish mathematicians created it or used it a lot a long time ago. You can read the Wikipedia article if you wish. So let's like try to process one of these. What about this 263 star plus? What does that equal? Let's take it step by step. What's the first step? Two times 6? I mean, you see, this 263 is different than this 263 because there's a star and a plus at the end in this order. So I believe what we would do here is we would say star. So that means 6 times 3. So now we have 2, 18 plus. So we essentially replace the 6 times 3 with the result, which is 18. So now we have 2 18 plus, and what's that equal? That's 20. So this represents 2 plus 6 times 3. Yeah?
How are we going to handle relationships? How do we know that it's not one?
We need to really have a separator kind of character so that we're not just storing straight digits, but chunks of numbers. How about this guy? Two 6 plus 3 star. Does that look familiar? It's not 20. Do you remember how we did this? So this is 2 6 plus. So you imagine when you find the operator, put it in between them. That's 2 plus 6, 8. And then 3 is now 3 times 8, or 8 times 3, 24. Does that make sense? So this is the 8, 2 plus 6, excuse me, 2 plus 6, and then times 3, which is 8. Whoa, that's right. That's cool. What? because in this format, the operators come after the operands. So let's do this. There were calculators a while back that used this notation. And where's that one? I was just wanting to see if we could come up with a big long one. I mean, really, we could do any set of numbers. I believe that you always have to have one fewer operations than operators than operands. Yeah? So I do that. Okay. So how will we process this? 14528 plus minus star slash.
We add 1 in to the data.
Okay.
And then we add 4.
Hmm?
Which means 8 dependent.
Okay, so notice what he's saying. Whenever we find numbers, we need to save them. We don't know what to do when we just have numbers. We really don't have our problem that's computable until we find an operator, plus minus star slash. So when we see the plus, this plus means what? Get the previous two operands, the 2 and the 8, and put the plus between them. Yeah? I think I'm going to do this step by step. So we essentially then take that 2, 8 plus and replace it with its result. So that's equivalent to 10. Okay? So we've just added a 10 to where it was. Now we look at our string and we've got a minus. What do we do with the minus? What do we do when we find an operator? Yeah. So we're going to imagine take the minus and put it between those two. So what's that? It'd be negative 5, right? Because our order does matter on subtraction and division. Okay. Okay. Sorry, so this is negative 5. It's not the minus, it's negative 5. Okay. We can find a star. What do we do when we find an operator? We find the last 2. So this is equivalent to negative 20. And then we found the slash, which is another operator. So we put it there, as it were, and it would be, right, yeah, negative. Good? You feeling this? So what data structure does that look like? Does that feel like? I think it's a stack or a queue or a deck or a linked list. It's not a linked list. You got your data structure in mind? I'd like to take a vote. See what y'all think. I like the commits. So I think a data structure is going to really help us implement this. You got your data structure in mind? Okay, how many people vote for stack? How many people vote for queue? Q. All right, we got 3 Qs. Dylan, did I get your vote? You're stack. You're a stack man. Okay. How confident do we feel? We want to wedge your push-ups on this? Very confident. Garrett, confidence level? No. As we're going through these numbers, think about, as we go through them, when we look at these 3 numbers, that's what we processed on, right? We had the plus, and then we looked at the 8 and the 2. So as we're processing them, are those the first numbers we saw or the last numbers we saw? Last. So we're going to be operating first on the last numbers that we saw. So the last numbers in are going to be the first numbers that get computed and kind of get put out. Does that remind you of anything? Remember this idea of last in, first out? What data structure is a LIFO data structure? This is the acronym that people use more. The first one in is the 1. The last one in was the 8. Like Philo apparently is a garbage name, but LIFO is cool. I guess they're putting the I first. There's another data structure that we call FIFO, which is the first in is the first out. What data structure is FIFO? That's a Q. Because that's fairness, right? First guy in is the first guy out. Stack, you could say it's not fair because it's a completely different thing. But that's the way we do stacks. That's how we stack up plates. You ever think that plate on the bottom is like really sad because he never gets used? Unless you have a really big party. But the guy that's on top just keeps being on top because it gets washed and put back on top. So this is a LIFO kind of operation because you're always looking at the last things, which is a stack. So this is a very stacky kind of thing. Yeah? So, and the beauty of this is it's really simple to do on a stack because you got 2 kinds of things. You have operands, numbers. Whenever you find a number, push it on the stack. An operator, plus, minus, star, slash, whenever you find one of those, then you know, hey, take the last 2 numbers and put this operation between them and do that operation, and then push that result back on the stack. So to walk through one of these examples, let's do our 2, 6 plus 3. All right, 2 is a number. What do we do with numbers? Put it on the stack. 6, what do we do with the 6? Push it on the stack. Oh, I missed them. It's star comes after this, my bad. Plus, push plus. No pushing plus. Nobody pushes plus around. What do we do when we find a plus? And in stack terms, what do we call that? In this case, we get to pop twice. The first pop is actually going to be the second number. The next pop is going to be the first number. And then the plus, you can imagine, goes in between them. So when we find the plus, we pop, pop, and put them in reverse order of the pops. compute this result. All right, what do we do with the number? 8. Push it. So I popped these two, so that takes it back to here. And then there's 8. Okay, so I'm kind of processing the string in one pass again. 3, what do we do with 3? Push it. And then we found a star. What do we do with a star? An operator. So we're going to pop both of these. Pop. The 3 becomes the second one. 8 becomes the first one. Do this map. And then just pop these two. So the stack is back to here. What do we do now? Push 24. We have now processed all of our symbols. There's no more to process. What does the stack look like? One element. This is good. This is what we want. Imagine that we had a 1 here. I don't know. Still following our rules. We just did the 24. There's still a 1 left to process. What do we do with the number? Push it. Now we're out of symbols. Look at the state of the stack. There's 2 numbers on it. What does that tell us? Something is wrong. It basically means this string is not a legal postfix notation. Yeah? Yep. And that's, there's an alternative problem as well, which I should just put in. You can imagine, I mean, in this case, it's like we have too many numbers. In other cases, that we have too many operations. So can I just keep going here, pretend like we're still processing? We got a plus, so pop the 2. So that's a 1 plus a 24, it's 25. So I pop those 2, and then push the 25. That was just the first plus. Now I go to the second plus. I pop, really, before I pop 1, I should check. Are there 2 things on the stack? If there's not, then there's something messed up. Or you could also catch it when you do the pop. If you ever pop from an empty stack, or try to pop, that means that's an illegal expression as well. You basically have more operations than operands. I would say just 1 number, because you process the operator. Yeah. How that numerically works out is there's always 1 fewer operators than operands. Additionally, I would want you to note, like this is one of the benefits of postfix. In postfix, you don't need parentheses because the order of the operands and operators actually defines the order that you're going to do it. So in infix notation, we have all those rules to say, hey, if you want to do the plus first, then you got to put parentheses around it because that breaks order of operations. Your order of operations are fully defined by the order of the symbols here, which is a kind of nice property so that you don't even need parentheses. But what if you wanted to do 2 times 6? But I'm saying that that particular operation can't be done in that order without parentheses in the way we do infix. So, yeah. Oh, here's some numbers here. Yeah, here's the big boy here that y'all can work through. Okay. Okay. Apparently, I did say I defined some of these weird special cases. Oh, did I just say return null? Okay, that's cool. This is, notice this method is a public static double question mark evaluate string s. So double question mark means null is a legal return value. So instead of returning something, like instead of throwing an exception, you just return null if something bad happens. So that would mean if you don't have enough operands, like here, if this is still the case, you don't have enough operands, you can't just do minus. I'm saying if you got nothing, return null. If you've got a bunch of spaces, return null. I mean, you could say a bunch of spaces just means 0, but apparently I said make it be null. If you just have one number though, that's legal, right? It's just you're gonna push it on the stack. It's gonna be the only thing on the stack. You're done. You feeling good about this? So I like this as it's really a relatively simple example that shows how you see, if you have a stack, this becomes a really easy algorithm. When you implement it, it's so easy. Like you got the 3 rules right there. If you don't have a stack, then I think what you'll end up doing is inventing a stack, or maybe you could just do it in a really convoluted way. But I think like it's clearly a stack. This is how this problem works. You just need to look at the last 2 things. Anything that came before you doesn't matter. Does not matter. You got to keep it in reserve, but you don't have to keep it in consideration for the current decision. Does that make sense? You can only look at, in this case, you only look at 3 things at the most. You look at your operand that you just found from this string and the previous 2 numbers, whether you call that 2 or 3. Okay, so those are both operations on a stack, or operations that are well suited to be solved by a stack. Okay, yeah, good. So that would be like this example here. Imagine, what's our stack going to look like at the end of this? What do you mean by the same? How tall is it going to be? 6 tall. Is that an okay way of ending one of these? There's only one way of ending that's legal, which is there's one. This stack can be 1 tall. It can't be 0. It can't be 2. It can only be 1, and that means we had enough of both to evaluate your question. Does that make sense? So like you can push all these on, and it won't know that it's wrong until you get to the end and your stack is too tall. You didn't encounter an error, but you ended in a state that's not legal. Okay. I would like to try a new assignment this year, and I want your help in defining it. So I would like everybody to get in groups of 2 if possible. Can you get a partner kind of person for a little in-class activity? It's just low-key. Give your participation grade if you want. More pieces of paper. How's that person? You can, I would say, since you're in a desk and a chair that moves, maybe you could like move a little bit closer to your teammate. Is that possible? I don't think that's going to lie. Okay. You guys seem to hate moving more than any other.
It's more that I can't decide.
Yeah, Josh, you and Jordan, you want to be team and then y'all move together? Oh, okay. Well, then move with Caleb. Okay, you get with Caleb, and you can join the team of. I've always said you were odd. Today you are. Join these guys. Okay. All right. I would like you guys to get out, open up some music app that you love to use, and look at a playlist. I'd like for you to look at the playlist on your music app of choice, or imagine one in your mind. And I'd like for you to, specifically talking about playlists, so when you have a set of songs. Music specific. I would like you to identify on paper, just write out all of the operations that a playlist supports. You follow me? All the things you can do with a playlist. I kind of went through this the other day. Remember this? This is what sparked my idea. Like there's definitely a thing where you can say, play this song next, and it like adds it to the current playlist. This is very Q-ish. So I'm thinking about what are the operations that typical apps allow you to do on a playlist. Does this make sense? There's a handful of things. And I'm sure everything does. Most of them have to do with ordering. It's more on the song, but I can see how we might look. So you can write it down. Oh, this is just participation. We're just getting some ideas down. Thanks for cleaning that up. That was You don't have to. Yeah. You just want to write it down on one sheet. That's fine. Try to identify what are all of the operations that a playlist supports. Like, I'm pretty sure most of them allow you to long press and like move a song anywhere you want, right? You with me? What can you do to a playlist? We need to be playing songs. It's completely appropriate.
So, so the things that we have, skip to the next.
So like Amazon. Yeah.
The I feel like we would be able to do that. But it just do a playlist.
There's definitely this reorder.
Suppose that it's fair. It's not just literally picking a random song.
Mine. Or the back. Your YouTube. Oh. So maybe you
Part of the problem having with this playlist is that if you actually make a playlist,
play that.
when you
I don't know if that's different.
So we just shuffle this way to make a new playlist. If you want to keep versus playlist.
Oh, so that's different. There's like a current queue. Okay, I see. Definitely include in this the idea of the current queue. If that's different from the playlist a little bit. I don't know, like I can play next. It's very queuish.
The problems that I was having with this is that with the playlist, you're going to want to keep the playlist. And so if we did something like a queue, it would a queue would remove things. So I was thinking that we could do it next time instead.
Yeah, so maybe I'm thinking when you play a playlist, it treats it kind of queue-ish, queue-like. Um, did y'all say anything about shuffle? Is shuffle a thing still? Okay. Mm. Shuffle. I think shuffle is an operator on this music playlist.
I think one of the hardest
Yeah, but check this. I mean, going forward or backward, previous next is an operation. That's fair. That can be on your list.
I'm just wondering how the
Well, we can do anything with enough time and effort, right? Thought.
like you put things on the that doesn't actually isn't actually a new operation. That's just play but do other things same song repeatedly instead of
Hmm.
would the ordering song be part of the operation for the playlist?
I think so. Doesn't that change what the playlist does? Like, but it's to me, it's like it's then the playlist going to the next song. Actually, is now the next song is the current song. Like,
I think that
so yeah. I have a very loose. I really am trying to look for a different set of operations in this space that we might implement on a data structure that's like a queue, but it's not exactly a queue. And then you've discovered them, and now we can decide whether or not to include them in the assignment. And I think loops are a really good one. I guess there's actually kind of two kinds of loops, right? There's like loop song and loop playlist, which then are both, I would say, operations on the playlist. It's like the playlist of currently playing songs.
I feel like being like just an operation, it would be looping, and you can have it where when you have looping single song, then that changes the move to next operation to where the move to the next song returns the same song you just played.
Mm-hmm. I can see that. It's still an operation that, like pressing the loop button, would have to be handled in some way.
Yeah. I'm just thinking about how we would handle it once we actually.
Enable native AOT publish. Okay. Y'all feeling good? Got some stuff? Okay. I'm going to kind of go sweep from left to right as I see the room, and I would like to hear the operations that you came up with, and then see if I want to add them to this fifth part of the assignment. Go ahead and tell me all of yours, and then y'all can fill in different things that you got. It's okay if we end up, you may be carrying the class here. What did y'all come up with? Okay. Add to playlist. Does that add in a specific spot? I mean, but it must add somewhere. To the end? Okay. Yeah? So that's a particular song. When you say order songs, is that like you long press and so this is like a how did y'all say this one? Move? Okay. Add to queue. What does that mean to you? So there's this, in my mind, it's almost like the currently playing playlist is special. it's more alive than the other playlist, right? And it has some special features. So when you say add to queue, but that's equivalent to like adding to the end, right? So play next makes it the
It's like if you have a playlist and you go to another playlist, you have just one song from that playlist to your next.
okay. And would you say this adds to the end or the beginning? The add queue. Add to queue. Adds to end. Play next then adds to the start, right? Or the front.
Well, play next seems to imply it's playing the song, and so in that case, it would play the top. Play the song.
Is this what you mean, Dylan? Play next plays it after the current song. Okay. Okay. Do y'all have one of these play next and add to queue? Those are the two that really put me on this whole thing. What else you got? Okay. Which is a lot like remove from playlist, but this is a specific playlist. Yeah. Okay, I like that. I'll clean this up. I think there's some shared logic that makes it so that we could actually kind of do both. We'll see. Okay, shuffle the playlist. Loop playlist. There's like a loop song too, right? Song in queue. Okay. So skip song is kind of like next. Is that what skip means? Okay. Play, pause. Solid. Okay, awesome. Thank you guys. What would y'all like to add to this?
I think that's pretty much. Oh, would you include like and delete?
That's fair. Yeah.
I feel like in this case, that would just be a new
And then like you can rename the playlist, like you can name it.
Yeah, that's a good add. That playlists normally have a name. Okay. Good. You got anything to add? Okay. I like that.
I'd already mentioned the using looping as a property, so those two loop playlists or loop songs would
Yeah.
change that property.
Yep. Anything else? Y'all got anything else? Anything new? Loop. So I got two loops. Yep. Good. Do you have anything else to add? Okay. So we're going to come back next time and see how we can use a queue to do some of this and start coding on this lab together. Stay strong. Hoko.